Assalamualaikum warahmatullahi wabarakatuh. My name is Nabihah binti Tajudin. So for today we will present the applications of computational mathematics in real life. Next, the table of content, both for application 1 and application 2, which is the SIR model and seismic model. We have the introduction, problem statement, how the mathematical models are constructed, application in Mathematica, and current issue. Application 1, the SIR model. Introduction, a population model is a type of mathematical model that is applied to the study of population dynamics. Models allow a better understanding of how complex interactions and processes work. Modeling of dynamic interactions in nature can provide a manageable way of understanding how numbers change over time or in relation to each other. Many patterns can be noticed by using population modeling as a tool. Ecological population model is concerned with the changes in parameters such as population size and age distribution within a population. This might be due to interactions with the environment, individuals of their own species or other species. Population models are used to determine maximum harvest for agriculturists, to understand the dynamic of biological inventions, and for environmental conservation. Population models are also used to understand the spread of parasites, viruses, and diseases such as COVID-19. The well-known words on the compartment SIR model paved the way for epidemiologists to mathematically describe the dynamic of infectious diseases and become increasingly popular among the scientific community, particularly for the analysis of current pandemic. These compartmental SIR models are composed of systems of differential equations that, except for a few cases, have no analytical solutions. Probably this is the main reason why only a very limited number of scientific works provide the fit of SIR type model differential equation system to the COVID-19 related data, and why others prefer to fit the data using approximated analytical expressions such as the logistic function. The number of daily new cases, decreased, and recovered related to COVID-19 is made available to the public in close real time, which makes it possible to test models by actually fitting the existing data. Fitting the solution of differential equations is undoubtedly a non-trivial process and usually requires extensive overhead work to implement dedicated software. Next, the problem statement. Since the first day COVID-19 was declared as pandemic, the cases keep increasing. Many efforts have been made by countries in the world to control the spread of it. One way that is commonly used in countries over the world is by going into mitigation phase, which includes putting the infected people under quarantine and starting the movement control order, followed by a lot of SOP. However, after taking such unusual actions to combat the pandemic, the case seems to be not going to stop. Following that, it is necessary to predict its trends. Government needs to know if and to what extent this initiative were successful. It is important to determine the path of this pandemic to plan for the steps that must be taken. Mathematical modeling, using either the deterministic or stochastic methods, is one of the ways to predict the trend of a pandemic. The deterministic model is based on the average characteristic of the population parameters under investigations, whereas the stochastic models consider the randomness of population element. In medicine, the most common modeling study is based on the deterministic compartment model. The SIR model are among the most applied deterministic model when examining the spread of infectious illness within a long experimental period. In this study, we are going to see how SIR models that are used by many experts are applied to determine the progress of COVID-19 pandemic in the world and for each country.
Next part is how mathematical models are constructed. Mathematical model that is chosen to study the modeling of COVID-19 is the SIR model. SIR model tries to predict things such as how a disease spreads, or the total number affected, or the duration of an epidemic, and to estimate various epidemiological parameters. In the basic SIR model, the total population is divided into three subsets, which are: S is the number of subsetical, which is the people who are not yet sick but who could become sick. I is the number of infected, which is the people who currently sick and recovered. R is the number of recovered or removed, which is the people who have been sick and can no longer infect others or be infected again. Ordinary differential equations or ODE of the basic SIR model are ds per dt equals to negative n to the power of negative n, di per dt equals to negative n to the power of negative 1 bsi minus ki, dr per dt equals to ki, where n equals to s plus I plus r is the total population, t is the elapsed time from the start date. ODE is used for the simulation to compute the variables after a short period of time. At any point of time, the ODE shows the rate of change for every variable. We can forecast the future by bringing together little changes over time. Thus, the SIR model is used for three main differential equations. Next, for mathematical model calculation, we use Mathematica. For first equation describes how the substatistical population changes over time. The second equation describes how the infected population changes over time. And the last equation describes how the recovered population changes over time. Then we set the parameter B and K. B is every 2 days, which is 0.5, and K equals to 1 over 14 days. Let the initial values at T equals to 0 for S, I, and R population. Set the value for I population is 0.0001 and S population is 0.9999. Next, to plot graph for SIR model, we use a command plot to see the movement of the SIR model graph. We also can use command plot legends to indicate three variables that we use, which are S, I, and R population.
The current issue for application 1, which is SIR model, when COVID-19, a new strain of coronavirus that causes a severe and potentially fatal respiratory illness, was discovered in Wuhan, Hubei province, China in December 2019. The COVID-19 pandemic in Malaysia moved from the alarm phase when the country became aware of the outbreak in China in late 2019 to the containment phase when the disease arrived in Malaysia in mid-January 2020. In this context, mathematical models are needed to estimate disease transmissions, recovery, fatalities, and other key factors individually for different countries, specific locations of high to low reported COVID-19 cases. In conclusion, this only underlines how invaluable this data is for all those who are currently fighting with the pandemic differential equation. Undoubtedly, it is very valuable for population models. Mathematical modeling theories are helpful tools for dealing with disease outbreaks, time dynamics, and patterns. They give us valuable prediction about the influence of action on lowering the number of infected susceptible incidence rates. Our SIR model, therefore, provides a theoretical framework for studying the COVID-19 virus propagation throughout communities. Next, we move to the second application, which is seismic model. So the introduction is nothing can stop a tsunami from occurring. They are extremely powerful natural disasters. One of the most common uses of differential equations is to describe the motion of multi-story structures that are subjected to earthquakes. The terrible damage caused by earthquakes in recent decades has motivated more research into earthquakes buildings interaction. The modeling was focused in simulating the movement of individual stories of certain simple two-dimensional construction that were subjected to strong vibrations.
Now let us see the problem statement of our second application. Earthquakes have long been feared as one of the most dangerous natural phenomena. Engineers need to consider and explain the impact of earthquakes on buildings. Reinforced concrete frames must meet the requirement of performance-oriented seismic engineering because the effects of damage must be considered when performing structural evaluation. Malaysia's engineer was were usually not concerned about seismic safety when designing structures. In their opinion, Malaysia is not a serious seismic zone, but Malaysia is surrounded by very active seismic bays to the west and east. Malaysia's west coast, Sabah and Sarawak, were exposed to localized moderate earthquakes. Between 1970 and May 2019, about 20 miles to moderate earthquake with a magnitude of over 3.0 MW were registered on the coast of Sarawak, and a magnitude of 5.9 earthquake struck Sabah on June 5, 2016, causing 18 climbers die on Mount Kinabalu. Damage caused by this earthquake includes rockfalls, landslides, and also cracks in buildings. Malaysia's maximum zone acceleration indicates that Sabah was in zone 2B and the maximum acceleration was between 0.10 G and 0.16 G. In Malaysia, the amplitude of the incoming seismic shear wave is generally small. The Malaysian peninsula is on the stable Sunda Shaft and seismic activity is low to moderate. Evidence show that Malaysia is not yet quake-free and they need attention to earthquake construction. The damage done to the building during the earthquake was associated with excessive displacement of building. Therefore, the design of the building structure is important to reduce the damage to the structure during an earthquake. How mathematical models are constructed for this application? In order to model the structural dynamic of a building consisting of n floors, we make some assumption. Firstly, the floor must have mass M1, M2, M3 until Mn. Each floor is assumed to be a point mass concentrated in the center of each floor. Then there is a damping force which is directly proportional to the damping constant C1, C2, C3 until Cn between the floors. A horizontal earthquake oscillation E cos omega t of the ground with amplitude E and acceleration A equal to negative E omega squared cos omega t produce a force which is F equal to ma equal to m E omega squared cos omega t on each floor of the building. This model can be used to analyze the phenomenon of building during an earthquake based on Newton's law of motion. The earthquake force E is given by Newton's second law. The earthquake's impact is determined by the natural oscillation frequencies of the flooring. And by using all of this, we will know the resonance effect between the incoming earthquake wave and also the building's floor.
Okay, for the next slide, mathematical model calculation. To illustrate the diagram for the earthquake of building, firstly, we use this manipulate command. We use AndySolve to insert the equation of the earthquake, which is Newton's law. Then, for the graph, we use graphics command for explaining the movement of the diagram. We use RGB color for differentiate the diagram. Lastly, for the indicator of diagram, we use this command, and for movement of diagram, we use autorun sequencing command. This is a rough model of the behavior of an idealized tall building undergoing horizontal seismic motion. The building has n floors supported by walls. Each floor has mass, but the weight is not taken into account. The displacement of the floors from their equilibrium position are S1, S2 until Sn. Initially, this displacement and their velocities are set to 0. Each floor experiences a restoring force from its contiguous floors according to Hooke's law with a spring constant K. The diagonal lines represent shock absorbers that introduce a damping factor gamma. There was an earthquake that happened in Saitama, Japan that made them involve acquaintance with this seismic event gives them an age. Seismographs are devices that record the ground's movement during an earthquake. It applies that the law of inertia that is also used when talking about buildings in an earthquake. When designing buildings and structures, engineers use the same basis with the earthquake shaking force that is based on Newton's second law of motion, which the equation is F equal to ma, which states that the initial force equals the mass times the acceleration to determine lateral seismic force. In conclusion, Newton's first and second law can be used to help Japan's engineers in designing buildings with the model's accuracy and dependability. Although a building may not collapse as a result of an earthquake, anticipating the damage that will occur can help to avoid disastrous outcomes. With the knowledge in system in differential equations, it helps countries having a safe house to live in that suits its natural phenomenal condition and location around the globe.